Okay, so can everybody see the slides and the transition?
I can.
Okay. Yeah, I think it's right time to start. So first of all, maybe you have saying the notice. Um, we're gonna uh, report the progress of our course project by the end of this month, and it's a kind of midterm course project report. And so I believe everyone has already made a decision, right? Someone has already made some submissions for Kaggle computation or work out the specific problem you want to explore in the exploratory project. So please make some progress and then submit the report uh, as we discussed at the beginning, right? So all the requirements regarding the reports, the limitation of pages, and are listed in our course web page. And please just refer to them, right? Okay, so let us continue with the perceptron algorithm. In the last lecture, we have introduced perceptron, right? Perceptron is essentially a learning algorithm for linear classifiers, right? And we assume, so here is just the standard framework. Let's just briefly review it. We assume the input is a sequence of training examples, x, y, y1, x2, y2, and so on, right? Where each training input, xi, belongs to the n-dimensional input space. The output or the label is either -1 or +1. So here I want to emphasize again, for convenience, when we talk about perceptron, their implementation, we assume all the bias parameter has already been folded into the weight vector. And meanwhile, the xi stays in the augmented feature space. Um, Namely, xi includes an extra constant feature 1, right? So our classification function is simplified as this inner product, right? Wt transpose xi, rather than plus b, because b has already been folded in this weight vector. So xi has augmented with constant feature 1, right? So here are the algorithm steps. We initialize our parameter vector w0 by 0 vector. And then we go through each training example, xi, yi. We first use our current weight vector to make a prediction on xi, right? So our predicted label is just take the sign of the classification function, which is this inner product, right? And then we compare our prediction with the ground truth, right? If the prediction is correct, then nothing happens. Nothing needs to do, right? We just look at the next training example. We only update our model when our prediction is wrong. Then here's our updating rule, right? We add the current weight vector, a product, which is the learning rate multiplying with the ground truth label yi multiplying with the input vector xi, right? We add this product to the current weight vector to get the updated weight vector. And after this update, we look at next example and make prediction and check if we have made mistake or not, right? If there's no mistake, look at next example. Otherwise, we make update and look at next example and go on until some stopping criterion is met. Right? And finally, we return the current weight vector. Right? So this is a whole perception algorithm steps. Right? So as we can say, this is a typical lazy learning approach. Namely, we update only when we make mistakes. Right? If our current model can correctly predict the training example, then nothing needs to do. Right? Nothing needs to do. We just look at next example. Right? So this is also called a mistake-driven algorithm. Right? So the K component of this perceptron algorithm comes from this updating rule. Right? So we have two cases when we made a mistake in predicting positive example, our updating rule is like this, right? We add Wt, the add rxi to wt because for positive example, yi is 1, right? If you make mistake in predicting a negative example, you're gonna subtract wt by the learning rate r times xi, right? Because yi here is -1. So then we give a very detailed analysis why this updating rule makes sense, right? So essentially, it always helps to improve the model. Like if your mistake is made because of your prediction score is too high, right? So after performing the update, your prediction score will be decreased so that you have a better chance to correct the mistake, right? If your mistake is because your prediction score is too low, then the update guarantees that the prediction score after the update gets increased, right? So that you have a chance to correct your mistake, right? So I also have showing this concept in geometry view, right? So I'm gonna escape those. And of course, perception is to learn a linear classifier only, right? So it cannot be used to learn a nonlinear classifier, right? A typical example is the XOR function, a more general parity function. But as we mentioned, like by applying appropriate feature transformation in a new higher dimensional feature space, you might still learn a perception, or you might still apply the perception to learn a separable or hyperplane. Right? Okay. So those are about the key details about perception algorithm, and hopefully everybody is comfortable with that and doesn't have any doubt about the meaning of the perception updating rule. Right? And then we'll talk about some kind of theoretical guarantee about perception. Right? This is called perception mystic bound.
Hey, sorry, I have one quick question about the algorithm.
Yeah, sure.
So the main loop is over each training example. So like I could imagine a situation where example 10 is going to end up moving the hyperplane boundary so that it now is wrong for like example 2.
Oh,
and so
this is not going through all the training example once. You can view it as like going through the training sequence again and again.
Oh, and so you just have some like, so then you could just have a stopping condition based on like the margin or whatever?
Yes.
Okay, so it's just, okay. So it's not like we're just running through at one time.
No, it's not. Okay. It's not like that. I'm sorry that because I'm gonna give some like a practical algorithm steps to implement this standard framework, and we'll discuss that later. But here you can just assume, okay, you pass through the sequence of training examples enough times.
Right. Okay. Just wanted to make sure on that.
Okay, thanks. And by the way, any other question regarding the algorithm steps? Okay, so then let us talk about the behaviors of running perception on different types of data set, right? So the good news is that if your data set is indeed linearly separable, and no matter how, in which order you feed the perception of the training algorithm, right, it guarantees to find you a separating hyperplane. In other words, the perception algorithm will converge. However, if the data set is not linearly separable, like the examples are labeled by XOR or any other parity function, and if you don't specify any meaningful stopping criterion, like if you don't make any mistakes, just quit, right? If you just keep running, it will enter an infinite loop. So you can imagine that there are a set of distinct weight vectors, and the perception is kind of like switching between those different set of different weight vectors again and again, and unless you enforce it to quit. So this is called cycling theorem. But of course, I mean, in practice, you always need to set some kind of hyperparameter, like how many updates you're gonna perform, and then you need to quit, right? No matter you really find a separating hyperplane or not, or how many passes you're gonna going through the data set, right? Which we're gonna discuss later, right? But the good thing is that, okay, as long as your data is has this good property, it's linearly separable, you can always find a separating hyperplane with perceptron. Then the question is that, how many updates do we need to find a separating hyperplane? From the perceptron algorithm, we know that we update model when only when it makes a mistake, right, in predicting the current training example, right? So the number of updates is actually the same as the number of the mistake made during the perceptron training, right? So today we're going to focus on how do we bound the number of mistakes made by perceptron in finding a separating hyperplane for a separable data set. So in the last lecture, we have introduced two very important concepts to introduce that theorem, right? So today I want to emphasize them again, because this concept, like margin distance, will be again and again used to illustrate the behavioral linear classifiers and their generalizer capability, generalizability, right? So what is margin? So the margin is originally defined as a property of a separating hyperplane, right? So we assume that the data set is linearly separable. When the data set is linearly separable, and also we have a separating hyperplane, which separate all the positive examples from negative examples. Then this hyperplane can have a margin. So the margin is the minimum distance between the data points in this data set and the hyperplane. So in this particular example, obviously, the point which is nearest to this hyperplane is this positive example, right? We just calculate distance, and this is the margin of the hyperplane for that data set. And we can further extend or generalize this concept margin to be as property for a separable data set. So if this data set is linearly separable, right, just like the data set here, right? So we can imagine that we have like numerous separating hyperplanes. We can rotate those hyperplanes, right, some kind of hyperplanes to some flexibly, and you see there are numerous, right? So we know that for each particular separating hyperplane, there's a margin, right? Then we pick up the largest margin of those separating hyperplanes as the margin of the whole data set. So again, using this particular data set, right, we can find many separating hyperplanes like these two dashed lines and solid line, right? So they all have different margins, right? But we know that for this for this solid blue line, its margin for this data set is the largest. So its margin is defined as the margin for the whole data set. We discussed in our last lecture, right? So margin of the data set actually reflects the separability of the data set, or the easiness to classify the examples in this data set, right? So the larger the margin, the further apart the positive examples from negative examples, right? So the easier you find a separating hyperplane. And then we review the how to calculate distance between any input, any point in this high-dimensional space and this on this separating hyperplane, right? So this is a general formula. I bet everybody has seen this formula before, so just list it here. But when we discuss and analyze behavior's perceptron algorithm, because we have used the notation simplification trick, where we have folded the bias B into W, right? So our hyperplane, our separating hyperplane, or the classification boundary is represented simply by this, right? Inner product is 0, right? And then by applying this standard formula to calculate the distance between an arbitrary point in the augmented feature space and this hyperplane, it will now become this. And when we calculate margin, all kinds of stuff, right? We assume, okay, this particular hyperplane can correctly predict all the training examples. meaning that we can simply replace the numerator, which is the absolute value of this inner product, right, by this product. The label, the actual label y0 multiplied with W transpose x0, right? Why? Because as long as W correctly predicts x0, this product is always non-negative. So this is something we have analyzed before, right? So we're going to use this trick again and again. And now it comes to our own trick, right? The mystic bound theorem, right? Very classical theorem in describing behaviors of perception, right? So basically, mystic bound theorem tells that in what kind of situations we can we ensure the convergence of the perceptual algorithm is ensured to converge, and the upper bound of number of mistakes it makes. Right? So first, the training examples, a set of m examples, right? X, Y, Y1, X2, Y2 to X, M, Y, M. Again, it's in augmented feature space, where each input vector or training vector is in n-dimensional space, and the length of each vector, or the Euclidean norm of this input vector, is upper bounded by R. The label is -1, positive one. Right? This is always true in practice, right? In practice, you're gonna never collect a feature input vector where the value is infinite, right? You don't represent the infinite value in the feature vector. Right? Just represent. Perhaps it's very large, but it won't be infinite. And this is first condition. Right? The first condition is that, okay, we require our training examples, they have a bounded range, or they have a maximum span, right? It's a limit span. It's a finite span. And about the second condition for this mystic bound theorem is the linear separability. So more specifically, we assume that there exists a univector U, right? And univector U can determine a separating hyperplane for this data set. And here we take a univector just to be convenient, nothing else. Which, and then that means, okay, the norm of U or the length of U is simply 1. Right? And we assume that associated with this separating hyperplane, there is some positive value gamma, and we have this product yi U transpose xi no less than gamma. So now I want to ask everybody, right? What does this mean? Right? What does the left hand side mean? What does the left hand side product reflect? Could anyone give us a hint? Anyone? We actually discussed about it in the last minute of our lecture Tuesday, right? Just to refresh our memory.
Isn't that the inner product of U and X is, I mean, that is just going to represent essentially, I mean, that's just the dot product. So, and then I guess when you multiply that by yi, it's basically saying, I mean, this is the distance formula from previous.
Yes.
And so based on that, we're just saying if we're looking at where the distance is greater than or equal to some threshold.
Yes, exactly, right. Thanks. So it comes to our calculation of distance, right? We mentioned that if W can correctly classify this particular point, x0, right? So we can replace the numerator by this product, right? And if for the normalized W to be a univector, so remember, univector has norm to be 1, right? So the denominator is simply 1, right? So this whole distance can be simply represented by y0 w transpose x0, right? So it's actually, in our case, w is replaced by this unit vector u, right? So just saying that, okay, there exists some, positive threshold gamma such that this product is no less than gamma for every training example, right? And this product, given a unit vector u, actually represents the distance between xi and the hyperplane determined by u, right? So this is saying that, okay, the training example, every training example, its distance from the separating hyperplane determined by u is lower bounded by gamma, right? So remember the definition of margin, right? Margin actually means the minimum distance between the training examples and the separating hyperplane. So actually gamma gives a lower bound of the margin. Right? So this is the second condition. Right? So given these two conditions, first, our data set has finite span, right? The norm of each input vectors are upper bounded, right? It's not like infinite large, right? Secondly, this data set is linearly separable and has at least one separating hyperplane with margin at least gamma, right? Then we can claim that if we run our perception algorithm in whatever order and the way you feed the training example, the algorithm will make at most this many mistakes on the training sequence before it finds you a separating hyperplane. So this upper bound of the mistakes is r over gamma squared. Right? So you divide the maximum span of the training inputs by the margin of the separating hyperplane and take square. So you can imagine this r is represent, okay, the range of the distribution, how the training example is distributed, right? And then gamma represents kind of like inner distance, right? If you separate positive and negative examples, what is distance between the nearest point and the separating hyperplane? You just divide them. Just divide the maximum range by this inner separability distance and take square. It gives you a upper bound of the number of mistakes or updates the perception algorithm will make. This is about a mistake bound theorem. So now to give a few more details, right? So I just want to emphasize, right? So first, all the feature vectors are augmented with a constant one. We emphasize again and again, right? Because our analysis and all algorithm frameworks are making such kind of assumptions. So don't be confused with our original definition of linear classifiers. And secondly, in practice, we can always find such an span or upper bound of the norm, right? You just look at the farthest data point from the origin, right? You just suppose you have like 10 or 100 training points, right? Just calculate the distance between any point and origin and pick up the farthest one, right? And use that to construct this R or to obtain this R. And thirdly, right, we just assume that the data is linearly separable and it has margin at least gamma. And one thing I just mentioned a minute ago, right? Why should we choose a unit vector u? It's just for convenience, not for any other purpose. We can definitely get rid of this assumption. Right? If we get rid of the assumption, meaning that u can be arbitrary with vector, then in our mistake bound, right, and it must contain the norm of u. So the final bound will look like this, right? So the norm of u times r over gamma takes square. So actually, our next homework, you might be required to prove this more general version, right? You don't have the unit vector assumption of u, right? And then how do you, what kind of mystic bound can you derive? Okay, so far, any question in understanding what the mystic bound theorem delivers.
Yeah, so on the augmenting our vectors to kind of integrate the bias, how did that work again?
You mean how does the notation simplification work?
Yeah.
Oh, here we just, okay. So this just means that, okay, each x1, x2, xm has some constant feature 1. So that your classification function is simply the inner product between the weight vector and the augmented feature vector. Does it make sense?
Not quite yet.
So basically, when we originally define the linear classifier, our classification function, let me write it out. Our classification function is simply W transpose X plus some bias parameter B, right? And it is not very convenient to write down this classification function everywhere. So in practice, people often use another representation, meaning that, okay, I'm gonna augment our feature vector with a constant feature 1, right? And then we append the weight vector. We append the bias parameter B to the weight vector. So we can redefine these two augmented vectors by some new weight vector and some new feature vector, right? In this way, we can write the classification function simply by W prime transpose X prime. That's it.
Okay, so B gets rolled into W, and then all of the x's have to have a 1 so that that gets paired up with the bias. I see.
Yes,
Okay.
exactly.
I noticed when we were talking about the margin, right? Like we were kind of moving around our hyperplane, like or trying to find the hyperplane with the correct, I guess, bias to get the maximum margin.
Mhm.
And then I realized that you weren't also like rotating the hyperplane because I think you could have gotten a larger margin that way. But does that not matter? Or back in the slide with the hyperplane getting the margin of,
Yes.
yeah, there we go. Yeah. So it looks like the kind of hyperplanes you're choosing between, those have different biases but have the same like slope, you could say. But I think if you have a vertical line, you'll get a larger margin. Is that kind of wrapped into how we're finding that hyperplane?
Well, you use vertical line to have a larger margin. It's not necessary, right? If you do the vertical line, it's like here, right? And your minimum distance um, between the training points, and it will be like this, right? Well, you might need to look at which one is smaller, right? But it should be this one. It should be this one. But conceptually, they're kind of like a. It doesn't change our any conclusion, right?
Okay.
Yeah. So the thing I keep reminding everybody is to because when we talk about this, right? When we talk about the separating hyperplane, when we talk about everything, is actually on the augmented feature space. That means in the augmented feature space, your separating hyperplane has this simplified form. It doesn't have speed. Why? Because B has already been folded in W. And so X always has constant features. So you can imagine that, okay, when we talk about in the augmented feature space, your separating hyperplane will now has to pass the origin. But all the training examples or test examples, they have a constant feature 1 as some coordinate. Does it make sense?
Yes, in the augmented feature space, it like shifts everything towards the origin, right, including the data.
Yes, exactly.
And so then all we care about is the angle, I guess, right? Like the other values, right?
Yes, yeah, because it's kind of like you fix a particular coordinate to be 1, because you have an augment x with 1. Right?
Okay, yeah, I think I see it.
Okay, great. Yeah. So, oh, by the way, any other question understanding the statement of theorem? Because next we're gonna show how we prove this theorem.
Yeah, I have one quick question. So if we're saying if it'll make, okay, so we're saying the perceptron algorithm will make at most r divided by gamma squared mistakes. So does that mean it's going to have that many updates?
No, it's just the upper bound. This is actually very loose upper bound.
Okay. But that's okay. That makes sense. Thanks.
It's just a very loose upper bound. So you can imagine that if the data set is linearly separable, there can be like infinite number of the separating hyperplanes, right? If you pick up any separating hyperplane, you pick up a different gamma, right? You actually have different bounds. So you actually might have construct an infinite number of upper bounds of mistakes. Okay, but anyway, we're gonna illustrate this bound. I mean, visualize that bound later, and we can come back to this point again. Okay, so a more succinct summary of mystic bound theorem is as follows. Right? Suppose we have a binary classification data set with n-dimensional inputs. In practice, we can always, for any such practical data set, we can always find a maximum span, right? Just look at the furthest data point to the origin, right? And second, if the data is separable, linearly separable, then the perceptual algorithm will find a separating hyperplane after making a finite number of mistakes. That's the kind of high-level idea what mystic bound delivers to us. And this finite number is upper bounded by this square of R over gamma. Okay, so now let us look into the proof. This is something very important. Perhaps this is this is just one. This is the only proof that requires everybody to understand, to know the details, right? And because it helps us to deeply understand the mechanism of perception algorithm. So we first look at the setting. So initially, we set v vector. So remember, this v vector also includes the bias parameter. Be zero vectors, be all zeros. And for convenience, we just set the learning rate to be 1, right? Obvious. But again, you can show the same conclusion by using an arbitrary non-zero positive learning rate. Perhaps it will be included in the homework, right? How do you extend that to include any constant learning rate R, right? It effectively skews the inputs but not change behavior. And then the two most important preconditions. First, all the training examples are contained in a finite ball of size R, namely their Euclidean norms are less than or equal to R. And secondly, the training data is separable by some margin gamma using a unit vector U. Mathematically, it is defined. It is expressed as this inequality for all the training examples xi, yi, right? So yi U transpose xi is no less than gamma, right? So to prove the mystic bound theorem, we're going to use 3 steps. So the first 2 steps gives our 2 inequalities, shows the 2 inequalities, and third step is to simply combine them together through a third inequality, and then we just solve a new inequality and to get this bound. So let us look at the first step. Right? So in our first step, we're gonna prove this claim that after t mistakes, this inner product, U transpose WT, is lower bounded by T times gamma. So U, remember, is the weight vector for some knowing separating hyperplane. Right? WT is the weight vector after T updates. Remember, in perceptron, after each mistake, we update the model. Right? After T mistakes, we denote updated vector currently by WT. Right? We're just saying, okay, the inner product between the weight of a separating hyperplane and the weight estimated by perceptron after T mistakes is no less than T times gamma. And gamma is a margin or lower bound of margin of this separating hyperplane. So how do we show this? We use the induction. So what is induction? Induction is just saying, okay, suppose at step t, right? So we will the number of mistakes t as some step, right? At step t, we assume, okay, your conclusion is right. Now we based on this conclusion to show that when we move to step t plus 1, this conclusion is correct as well. So this is our induction assumption, right? So we want to use this assumption to derive the same conclusion when we move to the next step, right? Meaning that we want to prove that U transpose WT plus 1 is no less than T plus 1 times gamma. Right? So let's see this. Let's see if we can do this, right? So we assume, okay, at step t, this inequality indeed holds, right? So now we want to check if after t plus 1 mistakes, right, at step t plus 1, right, this, if we can still obtain a similar inequality, right? Then we need to check the inner product between U and WT plus 1. Right? We know that WT plus 1 is updated from WT by applying this updating formula, right? So just substitute for WT plus 1 this updating formula, and then we can get this, right? So it's U transpose, because WT plus 1 equals to this, right? Equals to this, and then we use U transpose to multiply them. We get, it is U transpose WT plus YI U transpose XI. So now it comes from our pre-specified precondition, right? We know that U, the unit vector U, can well separate the training set, right? And its margin is at least gamma, meaning that the distance between every training point xi and the separating hyperplane determined by U is at least gamma. Right? So we immediately obtain a lower bound of this product. So we get the lower bound of this U transpose WT plus 1, right? Which is U transpose WT plus gamma. Right? So now, because of our induction assumption, we assume, okay, U transpose WT has already been no less than T times gamma, right? We merge them together, we get a lower bound of U transpose WT plus 1, which is T plus 1 times gamma. Right? Now we have shown that if the induction assumption holds, then the conclusion for the next step is correct as well. Right? Any questions so far? Okay.
So, what we've proved so far is that, like, so we should be done with the algorithm by the time we reach, the induction assumption, right? But say we were to go further, we've proven that the margin won't will only decrease, I guess, right? Or like it won't ever go above. Sorry, yeah, it won't ever go above gamma.
what we can see from this particular claim is just saying, okay, this angle between WT and U is lower bounded by this T times gamma, but I mean, it's kind of not very obvious to relate to the algorithm behavior, right? Well, what is position? But of course, this inequality does show some kind of a position constraint about WT. Right?
Mm.
But let us later like connect to the rounding behavior of perception. This is just to show this theorem. Okay. So any other question regarding the derivation of the steps? It's pretty, I think it's pretty straightforward.
Okay. You can keep going.
Right? Let's just keep this, right? So now we finished a very important step, a critical step, right? In the induction, we assume the induction assumption is correct. Then when we move to the next step, the induction assumption is still correct. That's a very important step, right? But the remaining step is just to check at first step, very first step, this induction assumption is correct again, right? Because starting from very beginning, if this induction assumption is correct, then following our derivation along with more and more steps, and each step is correct, then we can show that in the general case, all kinds of steps, the conclusion is correct. So what is the beginning of this step? When the number of mistakes T is 0, right? So when T is 0, we have W0, right? We know that W0 is 0. So the inner product between U and W0 is 0, right? So left-hand side here is 0, right? At the same time, because T itself is 0, the right-hand side is 0 as well. So I have verified that the beginning step, the induction assumption is correct, namely this inequality holds as well, right? And then according to our previous reasoning, right, at every step, because the previous step, the induction assumption holds, then at the current step, the induction assumption holds as well. And you just derive this from step 1 to step infinity. So we get the general conclusion that after arbitrary T mistakes, we always have this U transpose WT no less than T times gamma. This is how we show the first conclusion. Okay. Now let's look at the second step, right? The second step, we're going to use same kind of strategy to show another inequality. That is, after T mistakes, we have the square norm of the current weight vector upper bounded by T times R squared. So big R, remember, is a maximum span, right? A maximum length of the input vectors, right? So just saying, okay, after T updates, the square norm of our current weight vector is no bigger than T times the maximum length, square of maximum length of the training input. How do we show this? Again, using induction. We assume, okay, at step T, this holds, right? And then we look at whether it holds for T plus 1, right? So we look at the square norm of WT plus 1, and according to the updating formula, right, it is equivalent to the square norm of WT plus YI xi, right? So just expand this square norm, right? We know that it will have 3 terms: WT, the square norm of WT, the square norm of xi, and the cross term, right? So the cross term, you must have a scalar, a coefficient too, because it will appear twice if you directly expand them. So it's 2 yi WT transpose xi. So now we need to use our observation and understanding of the perception, right? So first, we know that according to our first pre-specified condition, right? We know that for each training example xi, its length is no bigger than r, so their square norm is upper bounded by r squared. Right? This is straightforward. But the second thing is us to capture the detail of the perceptron. So we know that perceptron only updates the model parameters when we make a wrong prediction. Meaning that WT plus 1 is obtained when WT makes wrong prediction of the label for XM. Right? So what does it mean? It means that this product must be negative. Right? We have discussed this trick before, right? So how do we test if our prediction is correct or wrong, right? We just look at the product of the ground truth label and the classification function, right? If this product is negative, it means that, okay, you must make wrong prediction, right? Because WT plus 1 is obtained only when WT make wrong prediction on this incoming training example, right? That means, okay, this product must be negative. So we have the second term less than 0, and third term less than and equal to R squared. Right? Then we can immediately get a bound, right? Upper bound, right? Which is the square norm of WT plus R squared. And then according to the induction assumption, we assume that, okay, WT squared, the square norm of WT is already being upper bounded by T R squared, right? And plus an extra R squared, we get a new upper bound for square norm of WT plus 1, which is T plus 1 R squared, right? So now I'm showing that, okay, if after T mistakes, this equality holds, you can show that after T plus 1 mistake, the similar inequality holds as well. Right? And again, we need to verify if this inequality is correct at the very first step where T equals to 0, right? T equals to 0, we know that left-hand side is 0, and the right-hand side is 0 as well because T is 0, right? So now we have proved the second inequality. Any questions so far understanding this proof? So it looks like everybody is comfortable, is happy with that. Okay, great. Yeah. Now we proceed to the final step. Right? So in step 1 and step 2, we have showing two inequalities. The first inequality is that after T mistakes, we have the inner product between the separating weight vector U and the current weight vector WT is lower bounded by T times the margin of a U, right, which is gamma T gamma, right? And the second conclusion, our second claim we have observed is that after T mistakes, we can upper bound it by square norm of the current weight vector by T times big R squared, right? And to connect them together, right, we first we start with the second inequality, right? If we flip the direction, right, we take the square root on both sides. We have R times square root T is no less than the norm of WT, or the length of WT, right? So now we want to connect these two inequalities. More specifically, we want to connect the right-hand side of this, right, which is norm of WT, to the left-hand side of the first inequality. How can we make such a connection?
Your screen share is frozen, at least for me. I'm not sure if it is for anyone else.
Can you say it again?
I think your screen share is frozen for me. I don't know if it is for anyone else.
Does anybody have a problem?
I also can't see your slides changing.
You can't see my slides changing? Oh, that's really bad. Okay, that's very frustrating. Let me stop sharing and do it again.
Yeah, I think it stopped for me after the first part of proof 3/3. So like everything was fine up to that point, but then it stopped updating.
Okay, yeah. Don't worry. Let me do it again. So I have stopped the sharing. I'll do it again. And so let me share screen again. Can everybody see the slides and transitioning?
I think it might still be loading for me. It says that you've started screen sharing, but I don't see anything yet.
Okay. Does it show up?
No.
Oh, that's weird. What's the problem with Zoom today?
It just appeared.
Now here it is.
Okay, so does the transition work?
Ah, yep. There's the r times the square root of t. And there's
Okay.
the
Okay. Okay. Hopefully it won't. I won't freeze again. Right? So do you see my drawing?
Yep.
Okay, great. I mean, continue with work where interrupted, right? So okay, we start with the second formula. We just flip the direction of the inequality and take square root on both sides, right? We get r times square root of t. T is never a mistake, remember? Okay, and is no less than the norm of the wt, which is length of current rate vector, right? Now we want to connect the right-hand side of this inequality to the left-hand side of the first inequality, right? How can we make such a connection? We're going to use the so-called Cauchy-Squarz inequality. So Cauchy-Squarz inequality has a very nice geometry interpretation, right? It's talking about how do we calculate cosine value between two vectors, right? So we know that for arbitrary two vectors, their inner product is equal to the product of their norms, right? Norm of u times norm of wt and the cosine value of their angle between the two vectors. Or in other words, like in vector algebra, we know that to calculate cosine value of the angle, cosine value of the angle between arbitrary two vectors, to just divide their inner product by the product of their norms. Right? So we know that cosine value is always less than or equal to 1, right? That means this inner product is always less than or equal to the product of their norms. But here in our case, the vector u is unit vector, meaning that their norm is 1. So now we immediately obtain that their inner product, u transpose wt, is less than or equal to the norm of wt. Okay? That's where we obtain here. Let's just flip the direction. Okay? And then the remaining thing is pretty straightforward, right? We know that according to the first formula, this inner product is further no less than t times gamma, right? So we can now connect the leftmost and rightmost terms because they both include our number of mistake t, right? So we just solve this new inequalities, right? Regarding to t, and we can derive that the number of mistakes t is always less than or equal to r squared over gamma squared. This is our bound, upper bound of the total number of mistakes. Okay, so any question regarding the third step, the proof in the third step? You just apply the Cauchy-Squarles inequality. That's it. Okay, so let's just read through this theorem again, right? To connect everything together, right? So this is a mystic bound theorem. We assume that, okay, first, all the training examples are kind of bounded. They have a bounded range. They have a maximum span R, right? And this data set are assumed to be linearly separable, meaning that we can find a unit vector U whose who determines the separating hyperplane and whose margin is at least gamma. And then we claim that by running our perceptron algorithm, it will make at most R over gamma square mistakes or updates before it finds a separating hyperplane. Oh, by the way, the separating hyperplane found by the perceptron is not necessarily the same as U. It can be totally different from you. Any questions so far? Great. So
yeah, sorry, one
Yeah.
quick question. So U is kind of like is the target hyperplane we're looking for.
no, U is not target hyperplane.
So what? Because I guess because I understand W is just a guess of the hyperplane, and we're updating that. But then I guess what does U represent?
You just represent any hyperplane that can separate data set. It's not necessarily the target hyperplane.
So when we take in this through this proof, as we take U transpose WT, what is that? What is that representing? Yeah, in here.
Well, you can imagine that, okay, this is your training example, right? So I'm just assuming, okay, there is some separating hyperplane represented by U, right?
Okay.
But when you run your perceptron algorithm, right, we're actually dynamic adjusting another hyperplane, right? And to finally lead to a position where it can also well separate the positive and negative examples.
So U is just an instant, just an example of a separating hyperplane.
Yes.
Okay.
And we just use U you can view it as a reference hyperplane or whatever.
Sure.
But U just provides some information that we can bound the number of mistakes or updates to adjust U, to adjust W.
Okay, that makes sense.
Yep. So this can be seen more clear from this visualization, right? So I guess that will be help us to understand the theorem even better, right? So suppose this is where our training examples are located, right? So positive examples, negative examples, and remember, and it's two-dimensional space, right? Just for convenience, and we can draw a ball, right? It's actually a circle, right? Which covers all the positive and negative examples, right? So its radius r is computed by the distance or the length between the furthest data point and the origin, right? So we get r, right? R actually represents the range of the training examples. And then, and to estimate the number of mistakes, the bound of number of mistakes, right? We're gonna find an arbitrary separating hyperplane, U, right? And from U, we know, okay, it has some margin gamma, right? Computed by the minimum distance between the data points and separating hyperplane. Right? And now we can use this range R and internal distance, right? Separating distance gamma to construct an upper bound of number of mistakes running perception. Right? No matter how, in whichever order you fit the training examples to our perception, the maximum number of mistakes it made before it finds a separating hyperplane is always upper bounded by this. But suppose we have our perception has made enough number of mistakes, and it finds a separating hyperplane. This found separating hyperplane is not necessary to be the black one. It can be another line or whatever other line. So this is what mystic bound theorem tells us. And someone may ask, okay, looks like I can construct many bounds, right? Obviously, yes. So we know that, okay, we use this black line and it's a margin to construct bound, right? I can construct a third bound, right? A second bound, right? I use this line, right, as our U. And we have a different margin, right? My different margin might be like this, right? You get a second gamma, say gamma prime. You can use gamma prime R to get another bound. So that means this bound is really a loose upper bound. In practice, the number of mistakes made by perceptions can be much smaller than this bound. What it implies that, okay, this upper bound is finite, right? Just guarantee you that okay, after finite number of updates or prediction mistakes, the perception will give you a separating hyperplane. Does it make sense? Any questions so far? Okay, great. Hopefully, everybody is kind of have no doubt, has no doubt about those theorem and how to prove that. Right? So next, we're gonna use this bound, right, to estimate number of mistakes in several specific function, and this is kind of a application of this bound. Right? So. The first exercise is to estimate the number of mistakes will the perception algorithm make for learning a disjunction with n balloon attributes. So assume the data set consists of all 2 to the n balloon input attribute vectors in the instance space. And the second exercise, which is gonna left for you guys, is to estimate the upper bound of mistakes to make when you learn a linear classifier to the k disjunction with n attributes. And we still assume the training data set includes all 2 to the power of n balloon variables. And we know that to get such a bound, right, the key thing is to find appropriate R and gamma, right? So now we now showcase how do we get this and for learning the conjunction, learning disjunction, right? So this is our target function x1, xn, right? We use this target function to label positive and negative examples in the n-dimensional input space, balloon input space, right? So the input is n balloon variables, right? N-dimensional balloon variables, right? To apply the mystic bound theorem to get upper bound of number of mistakes, right? Our first step is to find R, that is the span or maximum range of the length of the input vectors. Remember, when we talk about analyze perception algorithm, we're always putting the feature vectors in augmented feature space, meaning that all input vectors is augmented with constant feature 1, right? So actually, the input vectors are in the n+1 dimensional space with one constant feature, which is 1, right? And then what is R? R is actually square root of 1 plus n. Why? Any thought? Why?
Would it be because, so if every x value had a value of 1, that would be if we want to find the length of that, we would square all those distances, add them all together and square root it. But if we have 1 for every x value, that's going to be n. But then because we've augmented it, we have an extra 1. So we'll add 1 onto that, and then we'll take all those individual lengths squared and square root it to find that distance. And so that's why we end up with just the square root of 1 plus n.
Yes, exactly, right? Yeah, I just want to supplement one sentence, right? So R represents the maximum length, right? The maximum length of the input vectors, right? So maximum length of the input vector comes from the farthest point from the origin, right? In the n+1 dimensional space, which point is the farthest from the origin? The point with all x1 to xn takes 1, right? And because we augment feature space, we have an actual constant feature 1. So you can imagine the farthest point, its vector representation is actually 1, 1, 1, 1, 1, n+1s, right? So the distance from this all 1 n+1 dimensional vector to 0 is square root of 1 plus n, because we have n+1 elements. So this is our first step, right? We identify what is the range or what is the span of the training inputs. Right? So the next step is to find a separating hyperplane with some non-zero margin named gamma, right? So we actually have done this before, right? Or if right now you're doing homework too, you must be good at that, right? So let's just follow what the previous trick we have done, right? So this is a target function, right? The target function is a conjunction of n variables. We know that sorry, it's not conjunction, it's disjunction, right? We know that the disjunction is 1 if and only if any variable takes value 1, right? So equivalently, we could represent it as this inequality, right? Meaning that if the summation from x1 and xn is no less than 1, if and only if this, right, then the disjunction is 1, right? This and if and only and this inequality implies that at least one variable takes value 1, right? And then from this inequality, we can construct our equivalent linear classifier, right? We just move 1 to the left-hand side, we construct our separating hyperplane, which is summation from x1 to xn subtracted by 1 equals to 0, right? So now I want to ask, can we use this separating hyperplane to get a margin and use that margin to obtain the mystic bound?
Yeah, wouldn't this just be the case where W is equal to all ones and then B is -1?
Yeah, yeah, of course. You just want to confirm if it is usable, right? Can we use this? Imagine that this data set might have like many separating hyperplanes. We have found one with the easiest way, right? But my question is that can we use this separating hyperplane to get a margin and construct the mystic bound for the perception? Any thoughts?
We would want to take the distance between the hyperplane and all of the data points, right?
Yes.
I did have a different question though. So in this, are we assuming that the attributes here, like x1 through xn, are either 0 or 1 as their values?
Yes, Bloom variables, right?
Gotcha. Okay, because when I was doing the homework, I was assuming they were either -1 or +1. So I
No, this is about Bloom function. So the inputs are either 0 or 1s.
Gotcha. And that applies to the homework as well, right?
Yeah. When in the homework, when we say, okay, it's a Bloom function, that means the inputs can only take 0 or 1s.
Okay, cool.
So back to our question, right? Can we directly use this separating hyperplane to calculate the margin and then use that margin to get the mystic bound? Unfortunately, the answer is no. There's a small trap here, so just be careful. Because when we calculate the margin of this separating hyperplane, you will see the margin is simply 0. Why? Because some data points directly stay on this hyperplane. Which points, right? I can pick up an actual point, right? We can set x1 being 1 and all the other variables being 0. And when you evaluate the left-hand side, the classification function, you'll see it is 0. It means that, okay, this positive example, remember this is a positive example, right? Because it's conjunction, this disjunction. And that means this positive example directly lies on this line. According to the definition of margin, margin is the distance, minimum distance between the data points and the separating hyperplane, right? So if the point lies on this line, of course the minimum distance 0, right? Meaning that your gamma will become 0. And then we will construct the mystic bound, right? Remember, we divide the radius r by gamma, take square, right? Gamma is 0, meaning that, okay, you got a lower bound which is infinite, infinity, right? Infinity is not meaningful at all. Right? We know that, okay, number of mistakes is less than or equal to the infinity. It's not meaningful. Then how can we address this problem? Any thought? You just come, just any gas, wall gas.
Do we have to change the bias?
Yes, exactly, right. We can just move this hyperplane a little bit, right? We say, no, okay, this is our original hyperplane, right? Represented by this. And we know that, okay, this hyperplane is too close to all the training examples such that some positive example just stays on this hyperplane, right? So now, then why not we just move this hyperplane a little bit? How can we move that in parallel? Just like you said, right? We change the bias a little bit. So there are many choices right here. I just give you a simple choice where I just change the bias from -1 to -half. And now we'll look at first if this adjusted hyperplane still perfectly separate positive and negative examples. Second, if there are still some examples staying on the hyperplane. Right? So first, we would like to see if it can separate data set, right? So we know that all the positive examples will have at least one variable to be one, right? So if we evaluate this classification function, we see that all the positive examples will have this classification function at least 1/2. Why? Because at least one of variables in x1 and xn is 1, right? The one subtracted by half is half, right? If you have more variables to be 1, of course, your classification function value is bigger than half. Right? But as long as there is only one variable, you have a classification function value to be half. Right? This is for positive examples. So it obviously it will correctly classify all the positive examples. And then about negative, how about negative examples? We'll have one negative examples, which are 0, 0, 0, 0, right? So all the examples, all the n Bloom variables are taken 0. In this case, our classification function value is minus half. So obviously, it's less than 0. Sorry, forgive my bad drawing. Anyway, for negative example, the classification function is strictly less than 0, meaning that it can correctly predict negative example as well. Right? So from this analysis, we see that, okay, it can well separate all the positive examples, all the negative examples, for sure. At the same time, no examples has the classification function value to be exactly 0. Right? It means that no example stays on the new classification hyperplane. Right? That means we're gonna have a non-zero margin, right? Because the margin is a minimum distance between the training examples and the separating hyperplane. Now that there are no examples on the hyperplane, right? The margin cannot be 0. Right? And what is the margin? We just look at the point which is the closest to the separating hyperplane. Right? We actually have 2 points which are closest to separating hyperplane. Not 2 points, sorry, a few points, right? So the point, first the negative example will be closest to the hyperplane. Why? Because the left-hand side, absolute value of left-hand side is minimum, is half. For the positive examples, as long as only one variable takes 1, all the other variables take 0, you have the minimum absolute value of the left-hand side. That determines the distance, right? So it's still half. So then after the calculation, which I highly encourage everybody to calculate the minimum distance between the training examples and this hyperplane is this. Half over the square root n plus 1/4. Again, I encourage everybody to use this hyperplane to calculate its margin. Right? This margin turns out to be this by just applying some analysis and the standard formula we discussed before. Right? And then given the gamma and given the r, we can immediately create an upper bound of number of mistakes. Okay. So what you need to know about this mistake bound theorem, you need to know the meaning of this bound, right? And how to prove that. You need to be very familiar with details of proof. Okay. Okay, thanks for everybody. So in the next lecture, we're gonna wrap up the perception topic and by introducing several practical variants of perception. Okay, see you next Tuesday.